insight. Today, we are going to focus on linear regression. We're glad to have you here as we explore the important statistical method that help us understand relationships between different variables and make predictions. Today's lecture outcomes are to learn how to communicate with stakeholders, to learn and understand linear regression application in the real life, and lastly, to learn advantages and limitations of linear regression. The findings from Kaggle 2017 survey of data scientists highlight significant challenges that professionals face in the field, which are often not related to technical skills or recording. Instead, these barriers are categorized as last-mile issues, referring to the difficulties encountered in effectively applying data science insights in real-world scenarios. First, lack of management or financial support. Second, lack of clear question to answer. Third, result not used by decision makers. And lastly, explaining data science to others. In summary, this barrier emphasizes the importance of not only technical expertise but also effective communication, organizational support, and clarity in objective to ensure that data science efforts lead to impactful decisions and actions. Addressing these last-mile issues is critical for maximizing the value of data science in any organizations. So how to communicate effectively? First is to ask the right questions. Second is to speak in layman terms, especially to non-technical person. Third is to communicate often and clearly. And fourth, use right visualizations to send the message. In this slide, we focus on the line chart, a powerful visualization tool predominantly used in time series analysis. Line charts are essential for identifying trends over time, allowing us to observe how data points change at regular intervals. This makes them particularly useful for tracking metrics such as sales, stock prices, or website traffic. One of the key advantages of line chart is their ability to display multiple time series on the same graph. This feature enables users to see correlation between different datasets, helping to identify relationships and patterns that may not be immediately apparent when looking at individual series. For instance, by plotting sales data alongside marketing spend, we can assess the impact of marketing efforts on sales performance. In summary, line charts are invaluable for trend identification and comparative analysis in time series data, making them a staple in data visualization practices. The column chart, another essential visualization tool used to display data effectively. Column charts are particularly useful for showing changes over time or for presenting standalone data comparisons. Each column represents a category, and the height of the column indicates the value associated with that category, making it easy to compare different groups at a glance. One of the primary advantages of column charts is their ability to provide a quick display proportions. For example, if you want to compare the sales figure of different products over a specific period, a column chart allows us to visualize which product performed better and which how much. This clarity helps stakeholders make informed decisions based on the data presented. Additionally, column charts can be enhanced with color coding or labels to highlight key insights, making them not only informative but also visually appealing. In summary, column charts are a straightforward yet powerful way to communicate data changes and comparisons, making them a valuable tool in any data analysis toolkit. In this slide, we will explore the histogram, a crucial visualization tool used to display the distribution of dataset. Unlike other charts that represent individual data points, histograms group data into ranges or bins, allowing us to see how frequently data points fall within each range. This is particularly useful for understanding the underlying distributions of continuous data, such as test scores, age, or income levels. The primary purpose of histogram is to show population distribution, which helps us identify patterns such as skewness, modality, and the presence of outliers. Additionally, histogram also can help in assessing the normality of data, which is essential for many statistical analysis. In summary, histograms are a powerful tool for visualizing and understanding data distribution, making them indispensable in data analysis and interpretations. The box plot, a powerful visualization tool used to summarize and display the distributions of the dataset. Box plots, also known as a whisker plot, provide a visual representations of key statistical measures including the median, quartiles and potential outliers. The box in a box plot represents the interquartile range IQR, which contains the middle 50% of the data, while the line inside the box indicates the median value. The whiskers extend from the box to the smallest and the largest value within 1.5 times the IQR, helping to visualize the spread of the data. Any data point outside this range are considered outliers and are plotted individually, making it easy to identify anomalies in the dataset. Box plots are particularly useful comparing distribution across different groups. For example, if you want to compare test scores across different classes, box plots allow us to quickly see the central tendency, variability, and any other outliers in each class performance. In this slide, we will examine the scatter plot, a versatile visualization tool used to display the relationship between two continuous variables. Scatter plots are particularly effective for identifying correlation, trends, and potential clustering within data. Each point on a scatter plot represents an observation, with its position determined by the values of the two variables being analyzed. For instance, if we were to plot the relationship between our studied and exam score, each point would reflect a student's study time and their corresponding score. This visual representation allows us to quickly assess whether there is a positive, negative, or no correlation between the variables. One of the key advantages of scatter plot is their ability to reveal clustering patterns. By observing how points group together, we can identify distinct segments within the data, which can be crucial for segmentation analysis in marketing or identifying different behaviors in customer data. In this slide, we will discuss about the waterfall chart, which is a data visualization tool used to illustrate sequential impact of various factors on particular metric over time or through a process. The primary purpose of waterfall chart is to show how an initial value is affected by a series of positive and negative values, leading to a final result. This makes it particularly useful for understanding the cumulative effect of sequential introduced variables. A waterfall chart typically starts with a column representing the initial value. Subsequent columns represent increases or decreases in value, which are visually connected by lines. The final column shows the end results after the changes have been accounted for. Waterfall charts are commonly used in financial analysis to illustrate how revenue or profit changes over time due to various factors such as sales growth, costs, and expenses. In summary, the waterfall chart is a powerful visualization tool that helps communicate the sequential impacts of various factors on a key metric, making it easy for stakeholders to understand how different elements contribute to the overall results. So what is linear regression? Linear regression attempts to model relationship between two variables by fitting a linear equation to observed data. One variable is considered to be an exploratory variable or an independent variable, and the other is considered to be a dependent variable. You can think of linear regression as the answer to the question, how can I use X to predict Y, where X is some information that you have and Y is some information that you want to know. So linear regression is used for a wide array of business prediction problems such as stock predictions, predict future prices or costs, predict future revenue, or comparing performance of new products. The benefits of linear regressions are, first, ease. Linear regression is relatively simple to understand and implement. Mathematical concepts behind it are straightforward, making it accessible for practitioners and analysts. Second is interpretability. One of the significant advantages of linear regression is interpretability. The coefficients of the model provide clear insights into the relationship between the independent variables and the dependent variables. For instance, a positive coefficient indicates that an increase in independent variables leads to an increase in the dependent variable, making it easy to communicate findings to stakeholders. The third one is the scalability. Linear regression can handle large datasets effectively. As the size of dataset increases, linear regression can still provide reliable estimates, making it suitable for various applications, from small-scale studies to large-scale data analysis. The fourth one is deploys and performs well in online setting. Linear regression models can be easily deployed in real-time applications. They are computational efficient, allowing for quick predictions and updates as the new data becomes available. This makes them ideal for online settings where timely decision-making is crucial. Some of the examples of machine learning models that use linear regression approach are: first, simple and multiple linear regression. Second, polynomial regressions. Third, ridge regression and lasso regressions. Fourth, decision trees regressions. And lastly, support vector regressions. Let's take a look on how we can apply linear regressions in our examples. As we can see in the tables, there are a number of bedrooms and also their selling prices. This slide demonstrates a simple linear regression example that explores the relationship between number of bedrooms in a house on the x-axis and also its selling price on the y-axis. Each point on the graph represents a data observation showing the selling price of a house based on the number of bedrooms. The x-axis represents the number of bedrooms, ranging from 2 to 6 in this case. The y-axis represents the selling price in dollars. By looking at this, we assume that the number of bedrooms has a linear influence of the selling price. For example, as the number of bedrooms increases, we observe a trend where the selling price tends to increase as well. By using this data, we can do a linear regression model that can fit a line that predicts the selling price based on the number of bedrooms. This helps in estimating house price for homes not included in the dataset. Once trained, the linear regression model takes the form of linear regression equation, which is y equals to W0 plus W1x. Y is the dependent variable, the predicted value such as the selling price. W0 is the intercept of the line where the value of y when x is 0. W1 is the slope of coefficients of x, which is how much y changes for unit change in x. And x is the independent variable. In this example, is the number of bedrooms. These are the terms in the equation that we have discussed before. On the multiple linear regression, the main difference is the number of independent variables that they take as input. Simple linear regression just takes a single feature, while multiple linear regression takes multiple x values. Now we are exploring the difference between simple linear regression and multiple linear regressions, two fundamental techniques in predictive modeling and statistics. Well, linear regression involves one independent variable x and one dependent variable y. The goal is to find the best fit straight line that represents the relationship between these two variables. On the left-hand side of the slide, you can see how data points, orange dots, are scattered around a straight line. This line minimizes the error between observed data and the predicted values. For example, we might use simple linear regression to predict someone's income y based on their years of experience x. Moving to the right-hand side of the slide, we see multiple linear regression, which extend to the concept of simple regression. Here, we have two or more independent variables, example x1 or x2, predicting one independent variable y. The relationship is no longer a straight line but a plane or hyperplane as shown in the diagram. For example, we could predict income y using both years of experience x1 and education level x2. So how we can train on the linear regression model? We train the linear regression algorithm with a method named ordinary least square, OLS, or just least squares. The goal of training is to find the weights v in the linear equation y equals to W0 plus W1x. First, we do random weight initialization. In practice, W0 and W1 are unknown at the beginning. The goal of the procedure is to find the appropriate values for these model parameters. To start the process, we set the values of the weight at random or just initialize with 0. Next, we input the initialized weights into the linear equations and generate a predictions for each observation point. The residual sum of square, RSS, is calculated. What is residuals? Residuals or error terms are the differences between each actual output and the predicted output. And then we will do the model parameter selection to minimize RSS. Machine learning approach find the best parameters for the linear model by defining a cost function and minimizing it via gradient descent. The RSS serves as a measure of how well the regression model explains the data. A lower RSS means that the model predictions are accurate and the line of the best fit effectively captures the relationship between the independent and dependent variables. As the model trains, example using gradient descent, it adjusts the slope and intercepts of regression line to minimize RSS. When the RSS is minimized, the line fits the data as closely as possible. So what is cost function? Cost function is a mathematical formula that measures the error or differences between predicted values from a model and the actual values in the dataset. It is used to evaluate how well a machine learning model fits the data and helps guide the optimizations process to improve the model. Let's talk about gradient descent, a fundamental optimization technique used in training machine learning models. What is a gradient descent? It is a method to optimize the weight and bias of a model by minimizing the loss function or error. We start with an initial random value for weights, W, and iteratively adjust them to reduce the loss. So how does it work? At each step, we compute the slope of the cost function by taking the partial derivative with respect to the weights and bias. Then, based on the slope, the algorithm updates the weights, taking step closer to the minimum error. This process is repeated until we reach a minimum point where the cost is lowest. So what about the learning rate? If the learning rate is too small, the process will be slow. If it's too large, we might overshoot the minimum and fail to converge. So in this slide, the vertical axis shows the cost, while the horizontal axis shows the weight. The purple dots represent the steps taken to move from a random initial value to the minimum point. Each step is a result of adjusting the weights based on the gradient. So as a summary, gradient descent is an iterative process that helps optimize the model by minimizing the error. It is a cornerstone of machine learning training. Let's see on big learning rate. A large learning rate makes big jumps in the parameter updates. While this can speed up training initially, it often overshoots the optimal solution, which is minimum of the cost function, and fails to converge. In extreme cases, it can cause the cost to oscillate or even diverge. For example, think of trying to land a plane on a narrow runway but taking a huge jump forward each time. It is easy to miss the target entirely. A well-tuned learning rate takes appropriately sized steps toward the optimal solution. Steadily reduce the cost function without overshooting or taking too long. Imagine walking down a hill towards the valley at a steady pace. Each step gets you closer to the target without overshooting or hesitating. Too small running rates makes tiny adjustments to the parameters. While this ensures stability, it results in slow convergence, requiring more iteration and time to reach the optimal solution. In some cases, the training processes may stop prematurely, stuck in a local minimum, or take too long to improve meaningfully. Imagine walking down the hill but taking extremely tiny steps. You will eventually reach the bottom, but it will take much more longer than necessary. So how do we evaluate the accuracy of our model? We will use the mean square error, MSE, or the root mean square error, RMSE, or R2 or R squared or R2 score. In conclusion, this lecture has provided a comprehensive overview of linear regression, a fundamental statistical technique essential for understanding and predicting relationship between variables. We have explored the mechanics of training a linear regression model using ordinary least squares, emphasizing the importance of minimizing the residual sum of squares to achieve accurate predictions. Thank you for your attention, and I encourage you to apply these concepts in your future analysis and projects. See you in the next lecture. Bye!